Hello students, welcome to today's lesson. This is our third in the Fundamental Theorem of Calculus series, and this is actually a lesson that will include the second fundamental theorem of calculus. I'm going to start off with an example though that shows you a way to use the definite integral as a function. So in other words, using the definite integral to create an equation that you can substitute values into the x. So that can be accomplished by having the upper limit of integration as a variable. So when the upper limit of integration is a variable, you'll end up with a function that has x in it that you can then use in multiple ways. So let's take a look at this example. We have f of x equaling, and then we'll integrate from 2 to x. I'm going to go ahead and rewrite this as negative 2t to the negative 3 dt power. And then actually do the integration process on my next line. So using the power rule, we'll have negative 2t, your power would be negative 2. We'll divide by negative 2 and evaluate that from 2 to x. So I'm going to simplify, canceling out the negative 2's, and I'm going to rewrite the t to the negative 2 in the denominator with a positive exponent. So that'll be 1 over t to the second power, still evaluated from 2 to x. So now applying the fundamental theorem of calculus, where we do f of b minus f of a. Your b is the top limit of integration, so that would be 1 over x squared minus, and then 1 over 2 squared, which would be 4. So 1 over x squared minus 1/4. Now, with that, then as we change values of x, rather than our alternative, which would have been to integrate from, for this first x, from negative 2 to 2, and then doing a second problem integrating from negative 2 to 5, or excuse me, from 2 to 5, and our third problem integrating from 2 to 8, we instead have created a function where we simply have to plug in the 2 and the 5 and the 8 for the x into the already integrated function. So f of 2 is just 1 over 2 squared minus 1/4. And so that's going to be 1/4 minus 1/4, which will be 0. Now, that should make sense to you. As I said before, your alternative would have been to integrate from 2 to 2, and that would be an area of 0. So there's f of 2. You have another one, f of 5. And so for that, we would plug in 5. So 1 over 5 to the second power minus 1/4. So just a little bit more work with that. That would be 1 over 25 minus 1/4. Getting a common denominator of 100, you'd have 4 hundredths minus 25 hundredths, and that's going to be negative 21 over 100. So f of 5, negative 21 over 100. Let me make this 100 a little bit better. And then our last substitution, we have f of 8. And again, that is 1 over 8 squared minus 1 over 4. So we'll have 1/64 minus a fourth, getting a common denominator of 64. That'd be 16/64. And when you subtract, you get negative 15/64. So there's your first example. And again, sometimes it's more practical to use a variable as that upper limit of integration rather than doing the integration multiple times. So you'll see that is something that will lead us to the second fundamental theorem of calculus. So that's the next thing that we will take a look at. In the second fundamental theorem, let me scroll up. It says if f is continuous on an open interval I containing a, so now a is a constant. I want you to see that as we look at this theorem. So a is a constant, and that a has to be in the interval. Then it says for every x in the interval, the derivative with respect to x of the antiderivative of from a to x of f of t dt is equal to f of x. Now, that may not seem like that's very meaningful, but there will be cases where this will be helpful for us. And the gist of this theorem is that this constant value a is irrelevant. It can be any number a. So this a can be any number. And as long as it is a number in that interval, then when you do the derivative of the definite integral, all that would have to be done is substituting the x value into the function so that you get f of x. So you don't have to do any kind of a power rule. You don't have to make any changes to that function, but notice that you are doing the derivative of the antiderivative. So it's f with that upper limit of integration substituted in. So we do this when we want to get the derivative of the original function in terms of x. So we'll do a few examples, and we'll also do an illustration so that you can see the second fundamental theorem and how it works. So our first way that we're going to take a look at this is to just actually apply the theorem. So your example, find f prime of x, and that's probably something to take note of. You're finding the derivative when you're given an original function. So we're given an original function f of x equals, and it's the integral from 0 to x. So this 0 doesn't have to be a 0. It could be any number. So the integral from 0 to x of t cosine of t dt. I will make a note that the upper limit of integration must be a different variable from the one that you are writing in the integrand. So those two variables do need to be different. All right, so f prime of x would equal the derivative with respect to x of the integral from 0 to x of t cosine of t dt, and we'll simply plug in x everywhere there's a t, and so it'll be x times the cosine of x, and that's an application of the second fundamental theorem of calculus. So you have found the derivative of that antiderivative. So f prime of x would equal x times the cosine of x. All right, so let's take a look at an illustration of how this works, and maybe that will explain it a little bit better. So I'm going to clear this and scroll on up. Oops. So you'll have a few problems where you'll be given these instructions. You'll have to, first of all, integrate the function as a function of x, and then demonstrate the second fundamental theorem of calculus. So part A, we're going to just integrate the function. So here it says f of x equals the integral from 4 to x of t times t squared plus 1 dt. I'm going to rewrite this by distributing, because we cannot integrate a product. So I'll distribute. Please notice that my upper limit of integration is an x, but the variable that I'm writing in the integrand is a t. So I'm distributing the t to rewrite this as t to the third plus t dt. Then I'm going to do the power rule. So that would be t to the fourth over 4 plus t squared over 2. And then this is going to be evaluated from 4 to x. Again, I'm doing part A. It just said to integrate, so not applying the second fundamental theorem at all. So f of x, now I'm going to substitute in my x and then my 4. So I'll have x to the fourth over 4 plus x squared over 2 minus, and then I'll have 4 to the fourth over 4 minus 4 squared over 2. And so simplifying, f of x would equal x to the fourth over 4 plus x to the second over 2. And then minus, now my 4 to the fourth is, let's see, I did not do this one ahead of time, 256. That's divided by 4 to give me 64. So this part is 64 minus, and then 16 over 2 is 8. So, oh, excuse me, this is plus. I had my assignment, that is plus. So 64 plus 8, which would be 72, and so I'll get minus 72. So that is my function, f of x equals x to the fourth plus x squared, x to the fourth over 4 plus x squared over 2 minus 72. Now, that's part A. I have integrated the function so that I found it as a function of x. Now, in part B, it wants me to do the derivative. It says differentiate the result to part A. And by doing so, we're going to see that we could have just done the second fundamental theorem of calculus. So for part B, I'm being asked to find f prime of x. All right, so f of x that I'm going to use is the one that I integrated. I'm circling it. So I need to find f prime of x. And so thinking how you do a derivative, you're going to bring the 4 in front. So that'll be 4x to the third. And then that was over 4 plus, and then I'll have my 2, I'll bring in front, x over 2. And then my derivative of negative 72 is 0. And so this will simplify to x to the third plus x. Now I want you to look at this answer, that f prime is equal to x to the third plus x, and see that I could have started in part A and simply done the derivative f prime of x as, and then substituting this into both places, I would have had x to the third plus x without having to go all the way through and doing the antiderivative first and then the derivative second. So this is the second fundamental theorem provides you with a direct route from the antiderivative to the derivative. And you'll notice that this 4 that was my lower limit of integration could have been any number at all, because yes, I did get 72 in my function, but when I went to do the derivative, any constant is going to be a 0 when we do the derivative. So that's why this lower limit of integration, as long as it is a number, it can be any number. So there's your example to show that the second fundamental theorem of calculus does work. And then I'm going to do another one that actually just has you do the second fundamental theorem. So we'll do this one. It says find f prime of x, given that f of x is equal to the integral from 0 to x to the second of sine theta squared d theta. Now, I do have a note on this one that when your upper bound is a function, so notice that my upper bound is not just an x, but in this one it's an x squared. It says to make a substitution before applying the second fundamental theorem of calculus, and that's technically the way that you'll do it. But instead, I'm just going to make a note up here that we're going to do the chain rule. And when we do the example, I'll point out how the chain rule will work. So we're not going to actually make a substitution. We're going to do the chain rule. Again, this is anytime that your upper limit of integration is anything other than just an x. So applying the second fundamental theorem of calculus, f prime of x should equal, since we have a number as our lower limit and a variable as our upper limit, we should just be able to substitute in. So we'll have the sine of, now in place of theta, I'll put my x squared. The theta was squared. And then that would be the application of the second fundamental theorem. But now I'm going to do the chain rule because I had an x squared. So I'm going to multiply by the derivative of x squared, which is 2x. So your chain rule comes into play right here. This is the derivative of x squared. And that just multiplies there at the end. So f prime of x actually ends up being 2x times the sine of x to the fourth. And so you can see that if you are asked to find a derivative given an antiderivative, you can apply this second fundamental theorem of calculus. And so then if you'll turn your papers over, we'll be looking at the net change theorem. I'm going to do that on a separate video.